The ideal gas law may be rearranged to calculate the pressure, volume, temperature, or moles of an ideal gas. Hi, Mr. B here. In this video, I'll explain how to use the ideal gas law to perform a number of calculations involving an ideal gas. Okay, let's begin with a very simple ideal gas law practice problem. Given the following set of values, calculate the unknown quantity. The information given in the practice problem is as follows. The pressure, or P, is equal to 1.01 atm. The volume is listed as unknown. So for V, let's just place a question mark. The number of moles, or N, is listed at 0.00831. The temperature is indicated in degrees Celsius. So we're given 25 degrees C. When solving practice problems involving the ideal gas law, remember to write down all the givens and the unknown. One value not indicated in this particular practice problem is the value of R, where R will always be 0.0821 atm liters divided by mole K. To solve this particular practice problem, begin by rewriting the ideal gas law. PV is equal to nRT. The unknown quantity is the volume. So to rearrange the formula to solve for volume, simply divide through by pressure. This will generate the following formula. V is equal to nRT over P. Now simply insert the values, where V is equal to 0.00831 mole. R will always be 0.0821 atm liters divided by mole K. The temperature is given in degrees Celsius. However, in the ideal gas law, the temperature must be converted to Kelvin. 25 degrees C plus 273 will convert our temperature from Celsius to Kelvin. Now simply divide by the pressure, which is 1.018 Tn. At this point, it's convenient to cancel the units, where moles will cancel, atm will cancel. Converting the Celsius temperature to Kelvin, simply add 25 degrees C plus 273. This will convert the temperature to 298 K, which of course will now allow us to cancel the K's. This means that our final answer will be in units of liters, which indeed represent the proper units for volume. 0.00831 times 0.0821 times 298 divided by 1.01 will generate a final volume of 0.20 liters. Now for a slightly more complex practice problem. Suppose we're asked to determine the molar mass of a gas, given the following conditions: that 30 grams of the gas will exert a pressure of 253.25 kPa in a 3,000 milliliter volume at a temperature of 30 degrees Celsius. The first step in solving this particular practice problem is to recognize that moles are not given, only the mass. And the question is asking for the molar mass of the gas. Writing the ideal gas law, PV equals nRT, reveals that within the formula, a variable for moles is found. N represents the moles of a substance, in this case the moles of a gas, where the mole calculation indicates that the moles are equal to the given mass divided by the gram formula mass, or molar mass. Rewriting N as mass over molar mass will allow us now to solve for the molar mass. Since molar mass is in the denominator, to solve for molar mass, simply multiply through by molar mass. Multiplying through by molar mass will eliminate molar mass on this side of the formula and regenerate molar mass on the opposite side of the formula. The final step to solve for molar mass will be simply to divide through by PV. Dividing through by PV will eliminate PV on the left side of the formula and regenerate PV on the right side of the formula. However, this time PV will be found in the denominator. Now simply insert the given information. 30 grams represents the mass. R will always be 0.0821 atm liters divided by moles K. 30 degrees Celsius must be converted to K. To do so, simply add 273 to 30. This will equal 303 K. Now simply divide through by the converted pressure, where pressure is indicated at 253.25 kPa, which must now be converted to atm. So divide 253.25 by 101.3, and we will generate a pressure in atms of 2.5 atm. The volume is listed in milliliters. However, in the ideal gas law, the volume must be converted to liters. To do so, simply divide 3,000 by 1,000, which will equal 3 liters. To solve for molar mass, first cancel the units. G's will not cancel. However, K will cancel, ATM will cancel, and L will cancel, which means that our final units will be in grams per mole. 30 times 0.0821 times 303 divided by 2.5 times 3 will equal a molar mass of 99.5 grams per mole. The ideal gas law may also be used to determine the density of a gas. Consider the following. PV equals nRT. PV is equal to mass over molar mass RT. If D is equal to M over V, then according to the ideal gas law, mass over molar mass is equal to PV over RT. I'm simply isolating mass divided by molar mass from the ideal gas law. Also, mass over molar mass V is equal to P over RT. Since D is equal to M over V, then mass over volume is equal to molar mass times pressure over RT. Suppose we wish to determine the density of a sample of neon gas at 2 atmospheres of pressure and 298 K or 25 degrees C. To do so, simply use the rearranged version of the ideal gas law, where solving for D, mass over volume, is equal to molar mass times pressure divided by R times T. Inserting information will generate the following: 20 grams per mole times 2 atmospheres divided by 0.0821 atmosphere liter divided by mole K times 298 K. Canceling the units, where moles will cancel, atmospheres will cancel, and K will cancel, leaves us with the following units: grams per liter, which is also a unit for density. The final answer will be 1.63 grams per liter. Okay, this pretty much explains the ideal gas law. Mr. B here. Thanks for watching this video. Catch you next time. Take care.